Hello, and welcome to our presentation. I'm Brandon Skaggs from Cypress Semiconductor, an Infineon Technologies company, and I'm here to present our paper, Primary, Anonymous, or What? The Destiny of Ports from Design Top that Ultimately Are Driven from Off-Chip. This paper was co-written with my colleague Progyna Khondkar at Mentor, now Siemens EDA. For our agenda today, we'll begin with our motivation before discussing a few key concepts and sections within the UPF language reference manual that are relevant. We'll then proceed to our problem statement and test methodology before presenting our results and finally the conclusions we've taken from our data. So why are we discussing top-level ports? Obviously in verification we care about the inputs we provide our designs and our tests and whether the resulting output matches our expectations. But how do we account for the activity on these outer boundaries during power-aware verification? There are many contributing factors to whether and how we model corruption on top-level I/O. First of all, the characteristics of the top-level module itself plays a role. Is the top-level cell described as RTL or as a macro? Does the top-level design belong to a power domain? What types of I/O does it have? Secondly, the presence or absence of library or UPF attributes is a factor. What supplies are associated with a given I/O, and how does the behavior of the associated supply influence its corruption? Finally, semantic differences among UPF LRM revisions should also be considered. As we will see, the expected behavior of certain top-level I/O has changed as the language has matured and been clarified in newer revisions. Top-level I/O behavior will be inextricably linked to the behavior of their related supplies, and an incorrect association may cause unwanted corruption within simulation, or even worse, prevent corruption where appropriate. If our modeled behavior is incorrect because of wrongly attributed related supplies, this can lead to verification mismatches between RTL and GLS, increased verification turnaround time or iteration. It can lead to the incorrect implementation of supply networks and layout, or simply not catching an incorrect implementation. So ultimately, we're motivated to reduce the cost associated with this extra work. But how can we know what supply sets will be attributed to our top-level I/O? Will they be primary domain supplies, or so-called anonymous supplies? If they're anonymous, how will they model corruption? Are there any additional concerns if my design is a macro at the top level? What role will liberty or UPF attributes play in corruption? This paper presents empirical data based on an assortment of design top cases showing how each of these variables influence contemporary EDA linting and verification tools. As we said earlier in this presentation, we will review key concepts related to supply sets and port attributes. We'll discuss UPF LRM considerations related to supply semantics. We'll present the problem statement and the test scenarios we use to study this, and then finally we'll review our results and make some conclusions. Our first key concept is port attribution. Both the UPF LRM and Liberty library formats provide attributes that identify what power supply ports are related to a given I/O. Within the Liberty format, we have the related power pin, related ground pin, and another related bias pin attribute. Within UPF, we have the UPF related power pin, UPF related ground pin, etc., and these map directly to the Liberty attributes. We also have the UPF driver supply and UPF receiver supply attributes for associating with supply sets. In UPF, the attributes are assigned with the set port attributes command. The UPF related pin attributes are set with the related port options, and the UPF driver receiver supply attributes are set with the driver supply and receiver supply options, respectively. There is also a set of precedence rules that determine how conflicting attributes are resolved if more than one SPA command includes a given port within its effective elements list. Attributes can be applied to an assortment of candidates. For example, all of the ports on Module A. Or the command can filter and apply to ports of a specific type, as in all of the outputs of Module A. Or finally, attributes can be placed on the port directly. In this example, out1 is associated with VDD2 because it's a more specific rule and has higher precedence. The remaining outputs would be of Module A would be associated with VDD1, and then finally, any other remaining ports of Module A would be associated with VCC ACT. The IEEE spec governing UPF specifies a mapping of related Liberty attributes to UPF attributes. As stated earlier, the related power pin and related ground pin Liberty attributes map directly to the UPF-related power pin and UPF-related ground pin attributes. However, the mapping between these Liberty attributes to the UPF driver supply and UPF receiver supply is a bit more complex. The LRM states that if any of related power port, related ground port, or related bias ports is specified, an implicit supply set is created containing the supply nets connected to the ports. If the port being attributed is an input, the created supply set is treated as a receiver supply set. If the port being attributed is an output, the supply set is treated as a driver supply set. So in other words, stating the related power port of a design input is the same as specifying the receiver supply set. Inputs receive. Stating the related power port of a design output is the same thing as stating the driver supply. Outputs drive. This seems straightforward, but on the next slide we'll discuss the importance of hierarchical perspective to this idea. For our next key concept, we'll discuss what we really mean when we say driver or receiver. When we discuss a driver or receiver supply for a port, we may be talking about a characteristic of the design itself, or we could be saying something about the world the design lives in. Specifying a driver supply of an input, for example, or the receiver supply of an output, these describe something outside the design. But specifying a receiver of an input or a driver of an output describes an attribute of the port itself. Let's look at an example. The driver supply of the inputs of cluster A, noted in green, lie outside the design, as do the receivers of its outputs ports, marked here in blue. These attributes describe things providing input or receiving output from our design, and this is a perspective that we're comfortable with in verification. But when we describe a receiver supply of an input to cluster A, like this in orange, or the driver supply of its outputs in purple, we're saying something about these ports themselves. We're specifying the supplies that are connected internally to these I/O. In order to set proper expectations for how ports will be driving or potentially receiving corruption, we need to keep both perspectives in mind. The assumptions of how ports are attributed have changed over the timeline of UPF. An important clarification was introduced in UPF 3.1. In previous LRM revisions, it stated, if the driver supply is not defined for a primary input, or the receiver supply is not defined for a primary output, the default driver or receiver is assumed to be an anonymous supply that is not equivalent to any other supply. This is effectively a statement that a new independent supply set must be created for any I/O that isn't attributed. While this is easy enough to imagine and model in simulation, when it comes to implementation, this becomes an impracticality. Ultimately, on silicon, supplies are finite and known, and one of these must be assigned to provide power to the cells in question. So it's easy to understand the clarification made in UPF 3.1, which states, if the driver supply is not defined for a primary input, or the receiver supply is not defined for the output, the default driver or receiver is assumed to be the primary supply set of the top-level domain of the current scope. The assumption now is that the top-level domain supplies are associated with the top-level ports. But with many implementation tools not yet supporting the 3.1 standard, the question becomes, what do they do with the definitions they've been given in UPF-2? So now we come to the problem statement we discussed in our opening slides. Properly attributing the driver and receiver supplies of primary I/O is important to ensure adequate power verification. And we've identified 5 variables that influence how these attributes are applied to a design. The type of I/O, whether they're input, output, or in-outs. The type of design top, multi-rail macros or RTL. Specification of top-level power domain. Does the top level exist in a domain or not? The presence of applied port attributes. And then finally, what UPF LRM semantics were used. In order to examine the effects of these variables, we created a test matrix of 4 scenarios, varying the top-level design characteristic, whether it was RTL or a macro, and top-level inclusion in a power domain, whether the top level was included in the domain specification or not. Scenarios 1 and 2 share the design top characteristic of being an RTL design, but vary on whether the top level scope was included within a power domain. Scenarios 1 and 3 share top level inclusion in a power domain definition, but vary the design characteristic from RTL to macro definition. For each of these 4 scenarios, we created variations that use set port attribute commands to attribute related power pins or driver and receiver supplies. And we also created variations that changed what UPF LRM semantics were expected. Each test scenario was evaluated to determine how commercial EDA tools would attribute driver and receiver supplies. We used a commercial power-aware simulator that we'll call PA-Sim, and a commercially available static and linting tool that we'll call LP-Linter. At least 4 test variations were analyzed for each test scenario. We used one where no SPA commands were provided, and we used whatever was attributed by default. And the second, we used SPA to assign receiver supplies to input pins and driver supplies to outputs. In the third variation, we swapped this and attributed driver supplies for inputs and receivers for outputs. And then in the fourth variation, we assigned the related power pin, related ground pins, related bias pins attributes. Let's look at the results from scenario 1. For the first variation, when no SPA commands are provided, we see that the simulator attributes the input driver and output receiver supplies to be anonymous, as expected from the UPF-2 LRM interpretation. However, the linter takes the more pragmatic approach for implementation and attributes the unattributed supplies to the top-level power domain supply sets. In variation 2, we apply new attributes to the input receiver and output driver, but leave the unattributed input driver and output receiver as in variation 1. PA-Sim updates these as expected. However, LP-Linter continues to associate them with the top-level power domain supplies. For the case where the attributes are applied to objects outside the design, the previously unattributed supplies, both tools agree. Curiously, when applying the related power ground bias attribute, the linter continues to only apply the attribute to the external drivers and receivers, while the simulator properly maps the attribute to the LRM rule discussed in slide 8. Recall that scenario 2 is the case where the top-level scope is not explicitly placed in a power domain. Let's examine this case. Immediately we see that the LP-Linter does not allow the scenario where logic could exist in a hierarchy without any power domain to place it in. Such a scenario is not practically implementable. Buffers inserted at this level have to connect somewhere. For the case where no SPA commands are provided, PA-Sim anonymizes the input driver and output receiver supply sets as before. However, note the input receiver and output driver are also anonymous, since there are no supplies associated with a top-level hierarchy. It has no domain membership. For variation 2, we attempted to assign an input receiver supply and an output driver supply. However, only the output driver was updated. When we reverse the scenario in variation 3, we see the same inconsistency in that the receiver supply attribution fails. Finally, we see PASIM properly translate the related power, ground, bias pin attributes to driver receiver supply attributes. However, this results in the same scenario and results for variation 2. The input receiver supply is still anonymous. Summarizing the results for the remaining scenarios, we saw no impact when describing the top-level design as a macro. The results for scenarios 1 matched scenario 3 and scenario 2 matched scenario 4. Secondly, the UPF 3.1 semantics were not well supported. LP Linter errored out when specifying 3.1 as an option. However, as we found and discussed earlier, the 3.1 clarification was meant to aid implementation, and LP Linter did in fact assign top-level power domain supply sets in many cases where the older LRM would specify anonymous supply. So we could argue that in this case, it actually follows the intent. PASIM seemed to continue to use 3.0 LRM semantics and anonymize the supplies rather than associate them with the top-level power domain. Finally, we saw a big difference in the way top-level power domain attribution was handled in terms of error handling. LP Linter issued a warning and ignored the reassignment, while PASIM issued an error at the attempted reassignment, but allowed it after the error was suppressed. It's really difficult to know going in which tool is going to allow it and which isn't. So in conclusion, we can state that there's really no difference in behavior between macro and RTL scenarios. And for the most part, set port attribute commands attributed the inputs and outputs as expected. Both tools exhibited behavior that deviated from the expectations of the LRM. So caveat emptor, we really have to be careful. Finally, explicitly using driver receiver supply attributes on inputs and outputs independently is the best, most reliable method for ensuring clear specification of what can be expected for top-level I/O. Thank you for your time and attention to this presentation. We'll now transition to a brief Q&A session.